Let's talk about how to solve physics problems. Some problems can be solved with a single equation or single concept. Often these are easier problems for students to solve because if they know the equation that relates the variables involved or know the concept that relates them, then they can find the equation or concept in their notes and solve it for the answer. These are often the problems that students do well on, but I don't want to imply that these problems are always trivial. If you're applying a concept, you have to understand what the concept means, which can be nuanced. Or if you're applying an equation, you have to know the exact meaning of all of the variables in the equation and often have a conceptual understanding of the equation as well. As an example, if you're solving for work with this equation, work equals Fx times the displacement delta x, you have to know that the equation is only valid if the force is constant. And you have to know that these are the x components of the force and the displacement. So you have to define the x-axis in the direction of either the force or the displacement, and then use the x components of those vectors, which includes applying the correct signs. An equation like this can be challenging, so we shouldn't minimize the skills that it takes to apply it. But what I want to focus on in this discussion are the problems that involve more than one equation or concept. How can we solve the problems that are not just a single equation or concept? I'd say these are the problems that are more likely to cause a student to say, I don't know where to start. For these problems, the key is to first identify the type of problem that it is, and second, know how to solve that type of problem. Most of these problem types have procedures to solve them. It definitely takes knowledge and skill to execute these procedures, just like it takes skill to solve a single equation problem. Then you at least won't have to wonder where to start, and you'll have a framework for solving the problem. For the rest of this video, I just want to focus on this first step of identifying the type of problem. The procedures and techniques to follow are described in the topic videos and are demonstrated in lecture and posted examples, and students practice them in homework. The bigger challenge in my mind is often the first step of identifying the problem type. So here's a list of problem types for Physics 1. The list is actually not that long, so it's manageable, which is the whole point. If students don't categorize problems this way, then they can get lost in a sea of equations and concepts. There are 4 general comments I want to make about this list. First, the end of the list may vary a bit depending on the semester or summer term, especially the last 2 topics in the list, which may be dropped or replaced with other topics in a given term, but the rest of the list should be relevant. Second, recognize that these 4 topics, kinematics, the conservation of energy, the conservation of momentum, and Newton's second law, are generally considered the major principles in the course. These principles are used throughout the course in multiple scenarios and will also be used in Physics 2. Third, you can see that there are several applications of Newton's second law on the list. These are significant applications in and of themselves, and each one has a procedure associated with it. So I've listed them separately. And the fourth, notice that all of the angular and circular motion problems are captured by this list. Specifically, kinematics in the list also includes angular kinematics. The conservation of energy includes problems with rotational kinetic energy. The conservation of momentum also includes the conservation of angular momentum. And you can see that centripetal force and rotational dynamics both show up under the Newton's second law category. So now let's get to the goal of identifying which problem type applies to your problem. I suggest having this complete list on your equation sheet so you can scan through it when you need to. You can often decide which problem applies by the process of elimination. If the problem you're solving doesn't appear to be a single equation or concept, then it must be one of the topics listed here. So how can you identify which one it is? Some are easier to identify than others. Let's go down the list and tag the ones that are easier to identify, starting with the trip problems. You can identify that a problem is a trip problem because it involves a trip or journey or race or something like that that's broken into segments of constant or average speed. For example, driving a car at an average speed for an hour, then stopping, then driving your car at another average speed for another period of time. And then relative velocity problems can be identified by the fact that the velocities are referenced to or with respect to more than one object, such as relative to a moving car or relative to the Earth. Motion diagrams can be relatively easy to identify because they deal with time plots of position, velocity, and acceleration. Now let's skip the major principles and go down to simpler harmonic motion. These are identifiable because they deal with oscillating systems, and then waves, which include sound waves and resonance, is identifiable because it involves waves through a medium, and then fluids, whether static or dynamic applications, obviously involves fluids. So that leaves the four major principles, including all of the subcategories of Newton's second law. These are not always easy for students to identify. One of the first distinctions is that kinematics, the conservation of energy, and the conservation of momentum all involve an initial and a final state, or said another way, they involve initial and final positions of one or more objects. Conversely, Newton's second law applies to a system at an instant in time. So let's look at the categories of Newton's second law next, starting at the top. The basic scenarios are the ones we saw when we first were introduced to Newton's second law. They involve a system with multiple forces acting on it, potentially causing it to accelerate. In these applications, there may be forces with x and y components, there may be a normal force or friction, and there may be a slope involved. The tension scenarios are generally easy to spot because they involve strings, wires, etc. that cause a tension. In the static case, the system is not moving, so its acceleration is zero, and in the dynamic case, the system is moving and has an acceleration. The static equilibrium problems down the list are related to the static tension problems. In fact, the static tension problems are a subcategory of the static equilibrium problems. In both cases, the net forces in the x and y directions, according to Newton's second law, are zero. The distinguishing factor is simply that this principle alone is not enough to solve the static equilibrium problems. For static equilibrium problems, the principle that the net torque is also zero must be applied. It's difficult to come up with a simple rule to apply so that you know when the problems are one versus the other, but there are clues, such as static tension problems are often objects suspended by only strings and wires, etc., and static equilibrium problems often have other forces involved, like reaction forces from a wall. But neither of these is true in all cases. In the end, if you can't solve the problem with just the fact that the net forces are zero, then also apply the fact that the net torques are zero. Both principles are valid, so you don't have to worry about getting a wrong answer. Next, centripetal force scenarios often involve an object that is moving in a circular path, and we're analyzing the forces and linear acceleration of the object. Recall that the centripetal acceleration is a component of the linear acceleration. Rotational dynamics may also apply to an object that is moving in a circular path. The difference is simply the variables involved. Consider a carousel as an example. You could discuss the friction force on a person standing on the carousel, which would have a component of the net force in the centripetal direction. Or you could discuss the angular acceleration of the entire carousel and the net torque to accelerate it. So that's how we distinguish those scenarios for Newton's second law applications. Let's look at the remaining major principles. Problems that involve the conservation of momentum are usually not too difficult to recognize. The conservation of linear momentum problems involve multiple objects either colliding or recoiling. The conservation of angular momentum problems are similar. Multiple objects either collide, but rotational motion is involved, or a rotating object changes its moment of inertia, like an ice skater stretching out his or her arms to slow down. The very last two, kinematics and the conservation of energy, are interesting because there's an overlap. That is to say that some problems can be solved with either principle, while some problems can only be solved with kinematics and some can only be solved with the conservation of energy. For example, if you drop a ball from a meter and neglect air resistance, and you want to know how fast it's going just before it hits the ground, you can solve this with either kinematics or the conservation of energy. On the other hand, if you want to know how long it takes to reach the ground, then you have to use kinematics, because the energy equations that you use don't involve time. If you change this problem to include air resistance and are told that the work by air resistance is, say, -1 joule, then you need to use the conservation of energy, because in this scenario, the acceleration of the ball is no longer known, and in fact, the kinematic equations are not valid in this scenario because the acceleration isn't constant. So the main way to decide if you will solve a problem with kinematics or the conservation of energy is to consider the variables that are involved. If time is involved, then it's likely to be a kinematics problem. And if there are no vector angles given, or if the acceleration is not constant, then it's likely to be a conservation of energy problem. There's nothing wrong with trying to solve it one way and then realizing that you don't have enough information and switching gears and using the other principle. I personally try the conservation of energy first when I'm not sure, because it doesn't have a restriction like the acceleration must be constant, so I won't get a wrong answer, and I find that the math is often easier, though not always. The very last thing we'd like to discuss in this video is how to calculate work, because work can be very challenging for students. The first thing to consider is that work is always associated with a force. And the other thing is that there are only 3 ways that we have learned to calculate work in this course. Again, students will sometimes get stuck and aren't sure where to start. But if you remember that there are just these 3 equations that you can use, then you can get there by the process of elimination. Notice that each equation is associated with a particular force or a net force. If the force is constant, you can use the first equation. If the force is a conservative force, then you can use the second equation. Note that there are not many conservative forces in nature, and we only deal with 2 of them in this course, the gravitational force and the elastic or spring force, which we approximate to be conservative. In the third equation, we use the conservation of energy to calculate the total of all of the non-conservative forces. The second and third equations are mutually exclusive, because the force is either conservative or it's not. But the first equation may apply to a conservative or a non-conservative force. That is to say, a conservative force may be constant or it may not be, and similarly, a non-conservative force may be constant or it may not be. Also remember that the work is signed. These equations will give you the appropriate sign, but it's easy to make a sign mistake, so it's good to know what the sign should be conceptually. Here are the concepts to help you. The fundamental principle is that work is positive if the force adds energy to the system, and it's negative if it removes energy from the system. Sometimes it may not be obvious whether the energy is being added or removed, so there's another way to tell, which comes from the work equations, and that is comparing the direction of the force to the direction of the displacement. If the x component of the force and the displacement are in the same direction, then the force is doing positive work. Conversely, if those components are in opposite directions, then that force is doing negative work. And then there's the special case when the force and the displacement are perpendicular to each other, and then the force doesn't do any work to the system. That's the end of the discussion on how to solve physics problems. I hope you found this to be useful.